Welcome to The Drowsy Astronaut, and tonight we'll journey through every moon in our solar system, moving slowly from one world to the next, letting the details settle gently, like dust falling on an airless surface. This will be a long story spanning dozens of worlds, and we're in no rush to finish, so if you need to close your eyes and drift off at any point, or simply listen as you work, that's exactly what this is for. Before we start, I'd love to know where you're listening from tonight. Maybe drop a comment if you feel like it. It's always nice to imagine people from different places looking up at the same moon, sharing this quiet moment together. And if you're new here, or if these videos have helped you rest before, you're always welcome to subscribe. It truly helps us keep creating these calm journeys so you can sleep peacefully while exploring the cosmos. This isn't a lesson to memorize, and there's nothing here you need to remember tomorrow. Think of it more like floating beside someone who's describing the view out a window, pointing things out gently, never testing you on the details. What we'll do tonight is visit every major moon, from our own moon to the distant icy worlds. And we'll talk about what makes each one unique, what it would feel like to stand there, and what we might discover next. We'll discuss formation, geology, atmospheres where they exist, and the possibility of life. And I'll keep the language simple, explaining ideas before naming them, so nothing feels like a barrier between you and the universe. By the end, whether you're still listening or have drifted into sleep, your subconscious will have traveled through Jupiter's volcanic moons and Saturn's methane seas, through ice worlds and captured asteroids, through places where water hides beneath frozen shells, waiting for exploration. But for now, let's begin with the moon we know best, the one that's been watching over Earth for billions of years, pulling our tides, lighting our nights, the companion that's always there. What exactly is a moon? Well, it's simply an object that orbits a planet held by gravity, and our solar system has over 200 of them, ranging from tiny rocks to worlds larger than Mercury, each with its own character. Some moons formed alongside their planets, condensing from the same cloud of material, while others were captured later, asteroids or dwarf planets, pulled into orbit by a larger world's gravitational embrace. A few moons, including our own, were born from violence, from giant impacts that threw material into space, where it slowly gathered, cooling and colliding until a new world coalesced in orbit around the wounded planet. As we travel, we'll see frozen moons and volcanic ones, moons with atmospheres and moons with oceans. And we'll understand how each one shapes and is shaped by the planet it circles endlessly. Earth's moon is the fifth largest in the solar system, about 1/4 the diameter of Earth, large enough to make our planet-moon system almost a double planet orbiting a common center. It formed roughly 4.5 billion years ago, when a Mars-sized object that we call Theia struck the young Earth in a glancing blow, vaporizing rock and metal into a disk around our planet. That disk cooled and clumped together over perhaps a century or a millennium, and the moon condensed, still molten at first, glowing red in Earth's sky, so close that it filled 1/4 of the heavens, raising massive tides. Over billions of years, tidal forces pushed the moon gradually outward, and it now orbits at about 380,000 kilometers, still slowly receding at roughly 4 centimeters per year, a drift that continues today. The moon's surface is divided into two main types of terrain: the bright highlands, ancient and heavily cratered, and the dark maria, which are actually vast plains of solidified lava, filling ancient impact basins. When you look up at the full moon, those dark patches form the face we imagine. The seas that aren't seas, named by early astronomers who thought they might be water, but they're actually basalt, frozen flood lava. The highlands are older, dating back 4 billion years. Covered in craters from the late heavy bombardment, when countless asteroids and comets rained down across the inner solar system, scarring every surface. The Maria are younger, perhaps 3 to 4 billion years old, formed when massive impacts cracked the crust and molten rock welled up from below, flooding the basins with dark lava that cooled into smooth plains. Tidal locking means the moon always shows us the same face, because its rotation period matches its orbital period exactly, locked by Earth's gravity over millions of years, a common fate for close moons. So there's a near side, the face we see, and a far side, often wrongly called the dark side. But both sides receive equal sunlight, half the time in blazing light, half in frigid darkness as the moon turns through its month. The far side has fewer Maria, more highlands, and some of the deepest craters, including the South Pole Aitken Basin, over 2,000 kilometers wide, the largest confirmed impact structure in the solar system, exposing deep crustal material. Because the moon has no atmosphere, no wind or water to erode features, craters remain sharp for billions of years, footprints stay perfectly preserved, and the surface is a museum, recording every impact that ever struck it. Standing on the moon would feel strange and quiet. Gravity is only 1/6 of Earth's, so you could jump several meters high, and your steps would become slow bouncing leaps, pushing you forward in graceful arcs. The sky is always black, even at noon, because there's no atmosphere to scatter light, and stars shine steadily, visible all day, while the sun blazes as a brilliant white disk, harsh and unfiltered by air. Earth hangs in the lunar sky, for those on the near side. About 4 times wider than the moon appears from Earth, going through phases just like the moon does for us, but it never moves, fixed in one spot forever. The ground beneath your boots is fine grey dust called regolith, pulverized by billions of years of impacts, and it clings to everything, electrically charged by solar radiation, a challenge for any equipment or spacesuit that touches it. The Apollo missions from 1969 to 1972 landed 12 astronauts on the moon, and they brought back 382 kilograms of rock and soil, samples that revolutionized our understanding of lunar history, composition, and formation. Those rocks told us the moon's age, confirmed the Maria were volcanic, revealed the highlands are mostly anorthosite, a light-colored rock that floated to the top of the early molten moon, forming the first crust, like scum on cooling soup. We learned the moon is geologically dead, no active volcanoes or plate tectonics, just a cold, quiet world where moonquakes still occur deep in the interior from tidal stresses and thermal contractions, but the surface is still. Yet recent discoveries have surprised us. Orbital missions found water ice in permanently shadowed craters near the poles, hidden pockets that never see sunlight, where temperatures stay below -200 degrees, cold enough to trap frozen water for billions of years. This water could be crucial for future exploration, because hauling water from Earth is expensive, and having local resources means permanent bases become possible, using lunar ice for drinking, oxygen, and even rocket fuel made from splitting water into hydrogen and oxygen. NASA's Artemis program plans to return humans to the moon. aiming for the South Polar region where ice deposits lie, and the goal is not just to visit, but to stay, building habitats, testing technologies for Mars, and learning to live off the land. Imagine a lunar base nestled in a crater rim near the pole, with modules half buried in regolith for radiation shielding, solar panels soaking up sunlight that never sets at the crater's edge, and astronauts mining ice from the shadowed depths, extracting humanity's next foothold in space. The moon is close, only 3 days away by spacecraft, and it offers a testing ground for everything we'll need on Mars and beyond, making it not just Earth's companion, but humanity's stepping stone, the first place we'll learn to truly live away from home. Now, we leave Earth and move outward toward the red planet, where 2 small dark moons orbit close and fast, remnants perhaps of a captured asteroid or debris from an ancient impact, their origins still debated and uncertain. Mars has only 2 moons, Phobos and Deimos, named after the Greek gods of fear and panic, and they're tiny compared to Earth's moon, irregular potato-shaped rocks, more like asteroids than proper spherical moons, barely holding themselves together. Phobos is the larger, measuring about 22 kilometers across at its widest, and it orbits incredibly close to Mars, just 6,000 kilometers above the surface, closer than any other moon to its planet, zipping around in less than 8 hours. Because it orbits faster than Mars rotates, Phobos rises in the west and sets in the east, and tidal forces are slowly dragging it inward, pulling it closer to Mars, dooming it to crash or break apart in perhaps 50 million years, creating a temporary ring around the planet. Standing on Phobos would be surreal and disorienting. Gravity is so weak you could easily jump off into space, and Mars would loom enormous overhead, filling half the sky with its rusty red surface, deserts and canyons visible below, shifting position as Phobos races along its orbit. You'd see Mars rising and setting twice each Martian day, moving noticeably across the sky, and from Phobos you'd witness Martian sunrises and dust storms, watching the red planet turn below you, close enough to feel like you could fall onto it, pulled by its distant gravity. The surface of Phobos is dark, covered in a layer of fine dust and regolith, and it's marked by a massive crater named Stickney, nearly half the moon's diameter, an impact so violent it nearly shattered Phobos completely, leaving fractures that groove the surface. Deimos is even smaller, only about 12 kilometers across, orbiting farther out, taking 30 hours to circle Mars. And from Mars's surface, it looks like a bright star, not a disk, barely visible compared to Phobos, which appears about half the size our moon does from Earth. Future missions to the Martian moons include Japan's MMX spacecraft, launching in the next few years to orbit both moons, land on Phobos, collect samples from its surface and return them to Earth, helping us determine whether these moons are captured asteroids or impact debris. Phobos could also serve as a staging point for Mars exploration, a place to assemble equipment, refuel spacecraft, or rest before descending to the Martian surface, because landing on Phobos takes almost no fuel, and launching from there to Mars is easier than launching directly from Earth. Imagine a small base on Phobos, perched on the rim of Stickney crater, with modules anchored to the surface because gravity won't hold them down, and astronauts working in near weightlessness, assembling Mars landers, while the red planet dominates the view, rotating slowly, a world waiting below. The Martian moons are small and strange, not glamorous like the giants we'll visit next, but they're accessible, mysterious, and potentially useful, little stepping stones orbiting in the rust-colored sky, witnesses to Mars's long and changing history. Now we travel outward past the asteroid belt, toward Jupiter, the king of planets and the heart of the largest moon system in our solar system, where 4 massive worlds orbit alongside dozens of smaller captured rocks, each moon a world unto itself. Jupiter has at least 95 known moons, and more are discovered regularly. But 4 dominate the Galilean moons, named after Galileo, who first spotted them in 1610, proving that not everything orbits Earth, a revelation that helped overturn ancient ideas and reshape our understanding of the cosmos. These 4 are Io, Europa, Ganymede, and Callisto, and together they're like a miniature solar system, each distinct from volcanic hellscapes to frozen oceans, from radiation-blasted surfaces to ancient quiet worlds, offering more diversity than all the terrestrial planets combined. Tonight we'll visit each one slowly, imagining what it would be like to walk their surfaces, to see Jupiter's great red spot swirling overhead, to feel the pull of immense gravity, and to understand why these moons might hold the keys to finding life beyond Earth. Io is the innermost of the Galilean moons, and it is the most volcanically active body in the entire solar system, erupting constantly, with hundreds of volcanoes reshaping its surface faster than any other world we know, a landscape perpetually reborn. It's slightly larger than Earth's moon, about 3,600 kilometers in diameter, and it orbits very close to Jupiter within the planet's intense magnetic field, swept by radiation so fierce that it would kill an unprotected human in minutes, a deadly environment of charged particles and electromagnetic chaos. The surface of Io is a riot of colors: yellow, orange, red, white, and black, painted by sulfur and sulfur dioxide in various forms, freshly deposited by volcanic eruptions, giving Io the appearance of a cosmic pizza, mottled and strange, unlike any other moon. What makes Io so active is tidal heating, because Jupiter's immense gravity and the gravitational tugs of nearby Europa and Ganymede squeeze and stretch Io as it orbits, flexing its interior like a rubber ball, generating heat through friction, melting rock deep inside, and driving the relentless volcanism. There are hundreds of active volcanoes on Io, some erupting continuously, others in cycles, and volcanic plumes shoot material hundreds of kilometers above the surface, arcing through space in graceful fountains, because Io has almost no atmosphere to slow them, just thin sulfur dioxide gas that freezes and sublimates constantly. Lava flows on Io are hotter than anywhere else in the solar system, reaching over 1,000 degrees, some possibly made of molten sulfur, others of silicate rock like Earth's basalt, and they spread across the surface in rivers and lakes, glowing orange and red, cooling to black within days. One of the most famous volcanoes is Loki Patera, a massive lava lake over 200 kilometers across, regularly overturning its crust as fresh magma wells up from below, releasing enormous amounts of heat, making it one of the most powerful volcanic features anywhere, a cauldron of perpetual fire. Pele is another giant volcano, named after the Hawaiian goddess of fire, and it produces a persistent plume that rises 300 kilometers high, scattering sulfur dioxide across thousands of square kilometers, painting Io's surface with fresh deposits, a constant rain of volcanic snow. Standing on Io would be a nightmare scenario, not just because of the radiation, but because the ground could literally erupt beneath your feet, and you'd see molten lava flowing nearby, plumes shooting upward into the black sky, and Jupiter hanging enormous overhead, filling a quarter of the sky with its banded clouds and swirling storms. You'd feel Jupiter's gravity stronger than on any other moon, but still only a fraction of Earth's, about 1/6, and the ground beneath you would be fresh volcanic rock, sulfur frost, and ash, shifting and settling, never stable, never old, always being remade by the next eruption. The sky would be nearly black, with a thin haze of sulfur dioxide, and if you stood in shadow, you'd see stars, but also the glow of distant lava flows, orange spots on the horizon. And if you looked toward Jupiter, you'd sometimes see auroras flickering at its poles, energized by Io's own volcanic material feeding into Jupiter's magnetic field. Io is completely inhospitable to life as we know it. No water, no organic molecules, just sulfur and silicate rock, baked by radiation, melted by volcanism. A world that teaches us about tidal heating, about how moons can generate their own energy, about the violence gravity can inflict when planets and moons align just wrong. We will never colonize Io, at least not the surface, but perhaps someday from a shielded spacecraft in orbit, we'll study it closely, sending robots to sample lava, to measure heat flow, to understand the interior structure, learning how planets melt and how energy moves through worlds caught in gravitational struggles. Io matters because it shows us tidal heating in action. And this process is crucial because it might also warm the interiors of other icy moons, Europa and Enceladus, keeping subsurface oceans liquid, making those moons potential havens for life. And Io is the proof that tides can power worlds. Volcanic activity on Io continues to resurface the entire moon every million years or so, meaning there are no impact craters, no ancient terrain. Everything is young, refreshed by lava, and this constant renewal means Io's surface records only the present, never the past. A world without memory, only fire. As we leave Io behind, moving outward in our journey, we carry the image of that tortured moon, glowing faintly in the darkness, venting sulfur into space, feeding Jupiter's radiation belts, a world alive in the most violent sense, a reminder that the solar system is not quiet, not peaceful, but dynamic and sometimes terrifying. Next, we come to Europa, and the contrast could not be greater. Where Io is fire and sulfur, Europa is ice and water, a frozen shell covering an ocean, a world that might harbor life, a place that draws us forward with possibility, whispering secrets beneath its cracked and ancient surface. Europa is slightly smaller than Earth's moon, about 3,100 kilometers across, and it orbits Jupiter farther out than Io, still within the radiation belts but less intensely, and its surface is the smoothest in the solar system, covered in water ice that reflects sunlight brilliantly, shining like a jewel. The surface of Europa is crisscrossed with lines, fractures, and ridges, called lineae, that stretch for thousands of kilometers, and they're reddish or brown in places, colored by minerals or perhaps organic molecules brought up from below, staining the ice with chemistry we don't yet fully understand. There are very few craters on Europa, only a handful, suggesting the surface is geologically young, perhaps only 50 to 100 million years old, constantly refreshed by ice upwelling or resurfacing, which means something is active beneath, something is moving, renewing the ice, hiding older scars beneath fresh layers. Chaos terrain is another feature, regions where the ice has broken into blocks, rafts of ice that have shifted, rotated, and refrozen in new positions, like a jigsaw puzzle partially disassembled. and this suggests the ice shell is thin in places, perhaps only a few kilometers thick, floating on a liquid layer below. The evidence for a subsurface ocean is strong. Europa's magnetic field, measured by the Galileo spacecraft, indicates a conductive layer beneath the surface, likely salty liquid water, and tidal flexing from Jupiter heats Europa's interior just enough to keep that ocean from freezing, maintaining liquid water in the dark. Standing on Europa would be cold, brutally cold. Surface temperatures hover around -160 degrees Celsius, and the ice beneath your boots would be hard as rock, but smooth, almost glassy in places, cracked and ridged in others, a frozen sea that never melts, lit by faint sunlight and Jupiter's reflected glow. Jupiter would dominate the sky, even larger than from Io, nearly 24 degrees across, 11 times wider than our moon appears from Earth. And you'd see its storms rotating, its bands shifting, and occasionally the shadow of another moon transiting across its face, a slow celestial ballet playing out overhead. You might stand near a ridge, one of those long linear features, looking down its length as it stretches to the horizon, and wonder what force split the ice, what caused the surface to crack open, whether it was tides or ice expansion, or perhaps liquid water briefly exposed before freezing again, sealing the wound. If you were incredibly lucky, you might witness a cryovolcanic plume, a geyser of water vapor shooting up through a crack, sublimating instantly into the vacuum, reaching 100 kilometers high before falling back as snow. And though this hasn't been confirmed directly, Hubble has detected possible plume activity, hinting that Europa sometimes vents its ocean into space. Beneath that frozen shell, perhaps 10 to 30 kilometers down, lies an ocean that might be 60 to 150 kilometers deep, containing more liquid water than all of Earth's oceans combined. A vast dark sea, warmed from below by tidal heating, circulating slowly, potentially rich in minerals and dissolved salts from the rocky seafloor. This ocean is isolated from sunlight, completely dark. But on Earth, we've found life thriving in similar conditions, around hydrothermal vents on the ocean floor where hot mineral-rich water erupts from cracks, and chemosynthetic bacteria convert those chemicals into energy, forming the base of ecosystems that need no sunlight, no photosynthesis, only chemistry and heat. Could life exist in Europa's ocean? Perhaps near hydrothermal vents, if they exist, feeding on chemical energy from the rock-water interface. Simple microbial life, floating in the dark, reproducing slowly, sustained by Europa's internal heat, isolated from the universe above, a hidden biosphere that's persisted for billions of years, unknown and waiting. We don't know yet, and that's what makes Europa so compelling. It's not just a moon, it's a question, a possibility, a place where the universe might have experimented with life a second time, independent of Earth, and if we find even a single microbe there, it changes everything, proving life is not unique to our world, but perhaps common wherever water and energy exist. The Europa Clipper mission is scheduled to launch in the mid-2020s, a spacecraft that will orbit Jupiter and make dozens of close flybys of Europa, mapping the surface in detail, measuring ice thickness, analyzing the composition of any plumes and searching for the best landing sites, preparing the way for future missions that might drill through the ice and explore the ocean directly. Imagine the moment we receive images from Europa Clipper, Close-up views of the chaos terrain, clear pictures of the lineae showing their structure, perhaps even catching a plume erupting in real time, confirming that Europa's ocean is accessible, that we don't need to drill 10 kilometers of ice, just land near a vent and sample the water as it rises. Later missions might include a lander with a drill, or even a cryobot, a heated probe that melts its way down through the ice, descending slowly, lowering a tethered submarine into the ocean below, where it would drift in the darkness, lights on, cameras recording, searching for organic molecules, for movement, for any sign that we're not alone. Colonizing Europa is a distant dream, far more challenging than the Moon or Mars. The radiation alone would require massive shielding, and any base would need to be buried deep beneath ice or within caves. But the allure of that ocean is undeniable, and someday, perhaps centuries from now, humans might stand on Europa's surface, knowing an alien sea lies beneath, waiting to reveal its secrets. As we leave Europa and continue outward in Jupiter's system, we carry a sense of anticipation, because if Europa holds life, then the universe is teeming with possibility, and every ocean moon becomes a candidate, every icy world a potential cradle, and the search for life expands from Mars to the moons, from deserts to dark seas, transforming how we see our place in the cosmos. Next comes Ganymede, even larger than Europa, the biggest moon in the entire solar system, and the only moon with its own magnetic field, a world of ice and rock, ancient and young terrain side by side, hiding its own ocean deep inside, quieter than Europa, but no less fascinating, a giant among giants. Ganymede is enormous, larger than the planet Mercury, about 5,200 kilometers in diameter, and if it orbited the Sun instead of Jupiter, we'd call it a planet. But it's a moon, the largest satellite in the solar system, massive enough to differentiate into layers, with a metallic core, rocky mantle, and icy outer shell, structured like a miniature Earth. It orbits Jupiter farther out than Europa, taking about 7 days to complete one orbit, and from Ganymede's surface, Jupiter appears smaller than from the inner moons, but still impressive, about 14 degrees across, larger than a dinner plate held at arm's length, banded and beautiful against the black sky. The surface of Ganymede is divided into two distinct types of terrain: dark regions, ancient and heavily cratered, and bright regions, younger grooved terrain, covered in parallel ridges and valleys that stretch for hundreds of kilometers, suggesting some tectonic activity resurfaced portions of Ganymede long ago, perhaps 1 billion years in the past. The dark terrain is older, dating back 4 billion years, covered in impact craters that record the late heavy bombardment, and these regions are darker because they contain more rocky material mixed with ice, less reflective, absorbing more sunlight, holding the memory of ancient collisions that scarred the early solar system. The bright terrain is younger, perhaps 2 billion years old, and it's brighter because fresh water ice was exposed when the surface fractured and reformed, and the grooves suggest extensional tectonics, where the icy crust pulled apart, possibly from tidal heating or internal differentiation, creating patterns that look almost like Earth's fault systems, frozen in time. Ganymede is the only moon with a magnetosphere, a magnetic field generated by motions in its liquid iron core, and this field carves out a small bubble in Jupiter's much larger magnetosphere, partially shielding Ganymede from the worst radiation, though it's still a harsh environment, just less deadly than Io or Europa's orbits. This magnetic field creates auroras at Ganymede's poles, glowing ovals of light where charged particles from Jupiter's magnetosphere funnel down and strike the thin oxygen atmosphere, and from the surface you might see faint shimmering curtains of light, like Earth's northern lights but subtler, flickering in the near vacuum, painting the ice with ghostly colours. Standing on Ganymede would feel less alien than Io or Europa. The surface is solid, stable, ancient in some places, and the gravity is about 15% of Earth's, stronger than the Moon, so you'd still bounce when walking, but not as dramatically, feeling more grounded, more secure, while Jupiter watches from above, a constant companion. You might walk across the dark terrain, stepping over ancient craters, touching ice that's been frozen for billions of years, and then cross into the bright grooved terrain where the ground is smoother, ridges rising around you like low hills, parallel lines carved into the ice, and you'd wonder what forces shaped this place, what internal pressures pulled the crust apart and then locked it in place forever. Beneath Ganymede's icy shell, perhaps 150 kilometers down, lies another ocean, a layer of liquid water sandwiched between layers of ice, and this ocean might be 100 kilometers deep, salty like Europa's, kept liquid by tidal heating and residual heat from the core, insulated by ice above and below, protected from the cold of space. Ganymede's ocean is less accessible than Europa's, buried deeper, more insulated, but it's still there, and where there's water, there's potential. And though the energy available for life might be less, the chemistry could still support simple organisms, microbes drifting in the dark, feeding on minerals from the rocky mantle, surviving in isolation beneath 100 kilometers of ice. The JUICE mission, the Jupiter Icy Moons Explorer, is a European Space Agency spacecraft launching in the 2020s, and it will orbit Jupiter for years, studying Europa and Callisto, but its ultimate destination is Ganymede, where it will enter orbit in 2031, becoming the first spacecraft to orbit a moon other than Earth's, spending months mapping Ganymede in unprecedented detail. JUICE will measure the ice thickness, map the magnetic field, search for subsurface oceans, analyze the surface composition, and study the interaction between Ganymede's magnetosphere and Jupiter's, answering questions about how this giant moon formed, evolved, and whether its ocean could support life, laying groundwork for future missions that might land, drill, or even send probes into that hidden sea. Imagine someday standing in a research station on Ganymede, built near the equator where Jupiter is always visible. Modules connected by pressurized tunnels, solar panels and nuclear reactors providing power, and scientists drilling through the ice, lowering sensors into the ocean below, listening for chemical signatures, testing for organic molecules, slowly unraveling the mystery of what lies in that dark water. Colonizing Ganymede might be easier than Europa, less radiation, stable terrain, and abundant water ice for life support, and Ganymede's size and gravity make it a more practical long-term settlement, a base for exploring the entire Jovian system, a hub where spacecraft could refuel, where crews could rest between missions to the other moons, a foothold in the outer solar system. As we prepare to leave Ganymede and continue our journey, we look back at this massive moon, the king of satellites, larger than Mercury, magnetic and layered, hiding an ocean, wearing its history on its surface, a world that blends ancient and young, quiet and dynamic, a place that invites exploration and promises discovery. Now we move outward one more step in Jupiter's family, to the last and most distant of the Galilean moons, Callisto, a world entirely different from its siblings, ancient and quiet, bearing the scars of 4 billion years without healing, a museum of impacts frozen in time. Callisto orbits beyond Ganymede, about 1.9 million kilometers from Jupiter, far enough that tidal heating is negligible, and the moon never melted enough to differentiate fully, remaining a mixed body of ice and rock, layered but not separated, primitive and cold, unchanged since its formation. This distance also places Callisto outside Jupiter's most intense radiation belts, making it the safest Galilean moon for human exploration, with radiation levels only a fraction of what Europa or Io experience, a crucial advantage that makes Callisto attractive for future bases, despite its lack of geological activity or nearby excitement. The surface of Callisto is the most heavily cratered in the solar system, nearly saturated with impact scars, and new craters can only form by obliterating old ones because there's no space left. Every square meter bears the memory of ancient collisions, a battlefield that never healed, never refreshed, simply accumulated damage over eons. The largest feature is Valhalla, a multi-ring impact basin, about 3,800 kilometers across, with concentric rings spreading outward from the center, like frozen ripples in a pond, created when a massive asteroid struck billions of years ago, sending shockwaves through the icy crust, fracturing it in circles that remain visible today, a scar that spans nearly a quarter of Callisto's surface. Other large basins include Asgard, another multi-ring structure, and countless smaller craters cover every remaining surface, piled on top of each other, overlapping and eroding each other, though erosion here means only the slow accumulation of more impacts, micrometeorites, sandblasting the landscape over billions of years, smoothing sharp edges, atom by atom. There is almost no geological activity on Callisto, no volcanism, no tectonics, no resurfacing, just a dead, icy world that stopped evolving early in solar system history, and this stillness makes Callisto scientifically valuable because its surface preserves an ancient record, unmodified by internal activity, showing us what the early solar system was like when bombardment was constant and violent. Beneath the cratered surface, perhaps 200 kilometers down, there may be a subsurface ocean, though evidence is less certain than for Europa or Ganymede, based on magnetic field measurements suggesting a conductive layer, possibly liquid water kept from freezing by residual heat and antifreeze salts dissolved in the ice, a cold, dark sea beneath an ancient shell. Standing on Callisto would be profoundly quiet and still, the most peaceful place in the Jovian system, with no eruptions like Io, no cracking ice like Europa, no grooved terrain like Ganymede, just an endless cratered plain stretching to the horizon, grey and white, pocked and ancient, a landscape that speaks only of time and bombardment. Jupiter would appear smaller from here than from the inner moons, about 5 degrees across, roughly 10 times wider than our moon from Earth. Still impressive, but more distant, less dominating, and you'd feel farther from the giant planet's influence, more isolated, orbiting at the edge of its family, the quiet sibling watching from afar. The gravity would be weak, only about 13% of Earth's, so you'd bounce lightly across the surface, and each step would lift you high, arcing over small craters, and you might stand at the rim of a massive impact basin, looking across concentric rings that stretch beyond the horizon, frozen ripples commemorating a collision that happened before Earth's continents formed. This quietness and relative safety make Callisto ideal for a base, a place where astronauts could live with less radiation exposure, mining water ice for life support, using the moon as a hub for exploring Jupiter and its other moons, launching missions to Io or Europa from Callisto's stable surface, a way station at the edge of the storm, calm and dependable. Callisto teaches us that not all moons need to be active to be important. Sometimes stability matters, sometimes the ancient surface is the treasure, and sometimes the safest place is the most valuable, offering a refuge in a system filled with radiation, volcanism, and ice geysers, a quiet corner where humanity could one day build its first outpost beyond the inner solar system. Beyond the 4 Galilean moons, Jupiter has dozens of smaller, irregular satellites, captured asteroids and comets that orbit in distant elliptical paths, some retrograde, orbiting backward, and these tiny moons are dark, rocky, and irregular, tumbling through space, held loosely by Jupiter's gravity, remnants of the solar system's chaotic early days when capture was common and collisions frequent. We won't visit each of these small moons tonight, because they number in the dozens and more are discovered regularly, but they remind us that planet-moon systems are complex, with layers of captured objects surrounding the major moons, creating families within families, hierarchies of gravity and influence, small worlds orbiting larger worlds, orbiting a giant planet, orbiting the Sun. Now we leave Jupiter behind, moving outward through the solar system, and ahead lies Saturn, the ringed jewel, home to over 140 known moons, from tiny ring shepherds to Titan, the second largest moon anywhere, a world with an atmosphere thicker than Earth's, lakes of methane and chemistry that might teach us how life began. As we drift towards Saturn, we carry the memory of Jupiter's moons. Volcanic Io painting space with sulfur, Europa's hidden ocean whispering possibilities, Ganymede's magnetosphere carving a sanctuary, and Callisto's ancient scars recording history, 4 worlds that showed us moons can be as diverse and dynamic as planets, each a universe unto itself, each worth a lifetime of study. The journey continues, and Saturn waits ahead, its rings glowing faintly in sunlight, and around that ringed giant orbit, worlds of ice and methane, geysers and orange haze, shepherd moons and captured rocks, a system as beautiful as it is complex, beckoning us forward into the outer solar system where temperatures drop, distances grow, and mysteries deepen. Saturn has more known moons than any other planet, over 140 and counting, ranging from moonlets barely a kilometre across, embedded in the rings, to Titan, larger than Mercury, with an atmosphere and weather. And between these extremes lies a rich variety of icy worlds, each shaped by Saturn's gravity, rings, and the influence of neighbouring moons. The rings themselves are populated by tiny shepherd moons, small irregular bodies that orbit within or near ring gaps, and their gravity sculpts the rings, clearing paths, creating waves, and maintaining sharp edges, acting as gravitational gardeners that keep the ring structure organized, preventing it from spreading or collapsing over time. Pan and Daphnis orbit within gaps in the A-ring. Small moons only about 30 kilometers across, shaped like flying saucers with equatorial ridges formed by ring material that accumulated along their equators, giving them bizarre UFO-like profiles that look artificial but are entirely natural, sculpted by gentle collisions with ring particles over millions of years. Atlas orbits just outside the A-ring, another small shepherd moon, also with an equatorial ridge. And from close up, these moons would look surreal. Smooth, icy surfaces interrupted by a bulging waistline, like cosmic spinning tops, tumbling slowly, embedded in the glittering plane of Saturn's rings, surrounded by ice particles that sparkle in sunlight. Imagine flying past one of these shepherd moons, drifting slowly through the ring plane, particles streaming past like gentle snow, glinting in Saturn's reflected light. And ahead you see Pan or Atlas, a small irregular lump with that strange equatorial bulge, and beyond it stretches the vast ring system, arcs of ice reaching toward the planet, layers upon layers, creating a structure so thin and delicate, yet spanning hundreds of thousands of kilometers. The rings are mostly water ice, ranging from dust-sized grains to house-sized chunks, and they're remarkably thin, only about 10 meters thick in most places. Yet they extend from Saturn's cloud tops to twice the planet's radius outward, a flat disk of orbiting ice, perhaps the remnants of a destroyed moon or material that never coalesced, held in place by gravity and orbital resonances. Moving inward toward Saturn, we encounter the larger inner moons, starting with Mimas, a moon about 400 kilometers across, and it bears one of the most distinctive features in the solar system, the enormous Herschel crater, so large it makes Mimas look like the Death Star from fiction, though the crater formed billions of years before anyone imagined such things. Herschel crater is about 130 kilometers wide, nearly a third of Mimas's diameter, with a central peak rising 6 kilometers above the floor, and the impact that created it nearly shattered Mimas completely, sending shockwaves through the moon that created fractures on the opposite side, a collision so violent it almost destroyed the world it scarred forever. Standing on the rim of Herschel crater would be dizzying. Looking down into the vast depression, its floor far below, the central peak rising like a mountain, and beyond the rim, Mimas's curved horizon, and then Saturn itself, enormous in the sky, its rings slicing across the view, tilted at various angles depending on the season, casting shadows on the planet or shining brilliantly, reflecting sunlight back into space. Now we move outward to Enceladus, and here the story changes completely. From dead, cratered worlds to an active, icy moon that erupts with geysers, spraying water into space, and this tiny moon, only about 500 kilometers across, has become one of the most exciting targets in the search for life. A frozen world hiding a warm ocean, venting its secrets into the void. Enceladus is one of the most reflective bodies in the solar system. Its surface shines brilliantly because it's covered in freshwater ice, constantly replenished by the geysers, and that brightness makes it visible even in small telescopes from Earth, a tiny point of light near Saturn, reflecting more than 90% of the sunlight that strikes it, an icy jewel gleaming in the darkness. The surface has different types of terrain, cratered regions that are older, and smooth plains near the South Pole that are geologically young, barely cratered, covered in fresh ice and crisscrossed by 4 parallel fractures, nicknamed the Tiger Stripes, where the ice is warmer, thinner, and actively venting water vapor and ice particles into space through powerful geysers. These tiger stripes are only about 2 kilometers wide and 130 kilometers long, glowing faintly in infrared, warmer than the surrounding surface, and from these fractures erupt jets of water vapor, ice crystals, and organic molecules, shooting material hundreds of kilometers above Enceladus, some of it escaping into space to feed Saturn's E-ring, some falling back as snow, replenishing the surface with fresh ice constantly. The Cassini spacecraft flew through these plumes multiple times during its mission. sampling the material directly, and it detected water vapor, salt, silica particles, and complex organic molecules, including some associated with hydrothermal activity, suggesting that beneath Enceladus's icy shell lies a global ocean in contact with a rocky core where hot water circulates, dissolving minerals, creating chemistry similar to Earth's deep-sea hydrothermal vents. This discovery was revolutionary because it showed that a moon less than 1/10 Earth's diameter, orbiting far from the Sun where sunlight is faint, can harbour a warm liquid ocean kept from freezing by tidal heating from Saturn. And that ocean is not isolated, but connected to the surface through cracks, venting its contents into space, where we can sample it without even landing. Standing on Enceladus, near the South Pole, would be otherworldly. Watching geysers erupt from the tiger stripes, columns of vapor and ice shooting upward, backlit by Saturn's reflected light, creating ghostly pillars that rise and spread, and some of the ice would drift down around you like slow snow, coating your suit, replenishing the surface grain by grain, and above, Saturn dominates, magnificent with its rings, tilted at an angle that changes over the years. The gravity is incredibly weak, only about 1% of Earth's, so you'd barely feel weight, and jumping would send you arcing high, almost floating, and each footstep would lift you several meters, making walking difficult, requiring careful movements, and you might see other geysers in the distance, fountains of ice rising and falling, marking the tiger stripes that stretch across the southern landscape, fault lines into an alien ocean. Enceladus's ocean lies perhaps 30 to 40 kilometers beneath the ice at the South Pole, possibly thinner there where tidal heating concentrates, and the ocean might be 10 kilometers deep or more, warmed by friction as Enceladus flexes in its orbit, resonating with other moons, especially Dione, which locks Enceladus into an orbital rhythm that generates heat, keeping the ocean liquid despite the frigid temperatures above. The plumes contain organic molecules, salts from the ocean, and silica grains that suggest hydrothermal vents, places where hot mineral-rich water emerges from the seafloor, mixing with cold ocean water, precipitating minerals, and potentially providing energy for life, just as they do on Earth, making Enceladus not just geologically active, but potentially habitable, a tiny moon with enormous implications. Could life exist in Enceladus's ocean, perhaps clustered around hydrothermal vents? Chemosynthetic microbes converting minerals into energy, thriving in the dark, reproducing slowly, evolving over billions of years in isolation beneath the ice. And if so, we can sample them by flying through the plumes, catching cells or organic fragments vented into space, analyzing them for signs of biology without ever drilling through the ice. Future missions to Enceladus are being planned, including concepts for an orbiter that would repeatedly fly through the plumes, collecting samples, and possibly a lander that would touch down near the tiger stripes, analyzing surface ice for complex organics, measuring heat flow, listening for subsurface activity, searching for definitive proof that life exists beyond Earth, hidden beneath the ice of a tiny moon orbiting Saturn. The Enceladus Orbolander concept would combine an orbiter and a lander, spending years studying the moon from orbit, mapping the surface, measuring the ocean's depth, and then descending to land, deploying instruments, analyzing ice samples, maybe even drilling a shallow core, bringing us closer to answering whether Enceladus's ocean is sterile or teeming with life, whether we are alone or part of a cosmos filled with biology wherever water and energy meet. Colonizing Enceladus would be extraordinarily challenging but not impossible. The low gravity makes construction difficult, and the surface is frigid, but the geysers provide access to clean water. And if we could tap the tidal heating, we'd have geothermal energy, and a base near the South Pole could harvest water from the plumes, manufacture fuel, generate power, and serve as a research station studying the ocean below. Humanity's first outpost investigating an alien sea. As we leave Enceladus, we carry a sense of wonder and anticipation. This tiny moon, barely visible from Earth, has an ocean, active geology, and chemistry that hints at life, and it reminds us that size doesn't matter, energy matters, and wherever tides flex worlds and water flows, possibility exists, making Enceladus one of the best places in the solar system to search for life beyond Earth, a frozen shell hiding a warm secret. Now, we turn our attention to Saturn's largest moon, Titan, a world unlike any other satellite, the second largest moon in the solar system, the only moon with a substantial atmosphere, thicker than Earth's, a place where methane rain falls, rivers flow, lakes shimmer, and chemistry unfolds that might mirror the processes that led to life on Earth billions of years ago. Titan is about 5,100 kilometers across. Larger than Mercury, slightly smaller than Ganymede, and it orbits Saturn every 16 days, locked tidally so the same face always points toward the planet. And from Titan's surface, Saturn hangs in the sky, often obscured by thick orange haze that envelops the moon, hiding the surface from view in visible light, a perpetual fog that early astronomers found impenetrable. That haze is made of complex organic molecules, hydrocarbons formed when sunlight breaks apart methane in the upper atmosphere, and the fragments recombine into larger molecules, tholins, reddish-brown compounds that drift downward, coating the surface, giving Titan its orange glow and creating a chemical richness that makes the moon a natural laboratory for studying organic chemistry and prebiotic processes. The atmosphere itself is about 95% nitrogen, with a few percent methane and traces of other hydrocarbons, and the surface pressure is about 1.5 times Earth's at sea level, meaning you could walk on Titan without a pressure suit, though you'd still need a heated suit and oxygen supply because the temperature is around minus 179 degrees Celsius, cold enough to freeze methane and ethane into liquids. Titan has a methane cycle analogous to Earth's water cycle. Methane evaporates from lakes and seas, rises into the atmosphere, condenses into clouds and falls as rain, flowing into rivers that carve channels through the landscape, filling lakes and seas and then evaporating again, a continuous cycle driven by solar heating and weather patterns, making Titan the only world besides Earth where stable liquid exists on the surface. The lakes and seas are mostly liquid methane and ethane, and they're concentrated near the North Pole, with 3 large seas, the biggest being Kraken Mare, larger than the Caspian Sea on Earth, and dozens of smaller lakes, some temporary, evaporating and refilling seasonally, creating a complex hydrological system that shapes the landscape, erodes terrain, and transports organic molecules across the surface. In 2005, the Huygens probe, carried by Cassini, descended through Titan's atmosphere and landed, transmitting images and data from the surface, the first landing in the outer solar system beyond Mars, and those images showed a landscape of rounded pebbles, carved channels, and a murky orange sky, confirming that Titan's surface is shaped by liquid methane, flowing and pooling just as water does on Earth. Standing on Titan would feel strangely familiar yet utterly alien. The thick atmosphere would dim the sunlight to a twilight glow even at noon, and the air pressure would feel comfortable, almost like Earth, but the cold would be intense, deadly without insulation, and the gravity, about 14% of Earth's, would let you jump high, bound across the surface, while your feet crunched through organic frost and methane ice, surrounded by a landscape shrouded in haze. You'd see dunes in equatorial regions, vast fields of sand made from organic particles, blown by gentle winds into parallel ridges hundreds of kilometers long, dark against the icy surface, and if you traveled north, you'd reach the polar lakes, liquid methane seas stretching to the horizon, calm or rippled by wind, reflecting the orange haze above, and you might stand at the shore, watching waves lap against an icy beach, a coastline on an alien world. Rivers flow on Titan, carving valleys and channels, and some are hundreds of kilometers long, draining highlands and feeding lakes. And during Titan's long seasons, which last about 7 Earth years, weather patterns shift, and some lakes evaporate while others fill, creating a dynamic system that changes over time, sculpting the surface, moving methane around, creating landscapes that evolve, unlike the static surfaces of airless moons. There are also mountains on Titan, rising over 3,000 meters, icy peaks made of water ice as hard as rock in the cold, and there's evidence of cryovolcanoes, ice volcanoes that erupt not lava but liquid water mixed with ammonia, flowing briefly before freezing, and these eruptions might bring material from Titan's subsurface ocean, if one exists, mixing internal chemistry with the surface, creating complexity and diversity across the moon. Beneath Titan's icy crust, perhaps 50 to 100 kilometers down, there may be a subsurface ocean of liquid water kept from freezing by tidal heating and radioactive decay in the core, and this ocean, if it exists, would be isolated from the methane lakes above, separated by a thick shell of ice, creating 2 completely different liquid environments on one moon, one cold and hydrocarbon-rich on the surface, one warm and water-rich below. This dual environment makes some scientists wonder if Titan could host 2 forms of life, one based on water chemistry in the subsurface ocean, like life on Earth, and another based on methane chemistry on the surface, a completely alien biochemistry that uses liquid methane as a solvent instead of water, metabolizes hydrogen instead of oxygen, and exists at temperatures where Earth life would freeze solid instantly. We don't know if such methane-based life is possible, but Titan's surface chemistry is complex, with organic molecules accumulating, reacting, forming polymers, and if life can adapt to use methane, Titan offers an environment where it might thrive, making this moon not just interesting geologically, but potentially a laboratory for alternative biochemistry, showing us that life might be more flexible, more creative than we imagine. Colonizing Titan might be easier than any other outer solar system moon, because the thick atmosphere protects from radiation. Landing and takeoff don't require vacuum-rated systems. The surface pressure is manageable, and abundant hydrocarbons could be processed into fuel, plastics, and energy, making Titan resource-rich and relatively accessible, a prime candidate for future human settlement in the distant future. The Dragonfly mission, scheduled to launch in the late 2020s, will arrive at Titan in the mid-2030s, and it's a drone, a rotorcraft that will fly through Titan's thick atmosphere, hopping from site to site, exploring diverse terrain, analyzing organic chemistry, searching for prebiotic molecules, and studying whether the conditions that led to life on Earth might be replicated in Titan's hydrocarbon lakes and organic-rich surface, a mobile laboratory seeking the chemistry of life's origins. Imagine the data from Dragonfly, aerial images of methane seas, close-up views of dunes and river channels, chemical analysis of surface materials, and perhaps discoveries of complex molecules, amino acid precursors, or structures that hint at processes we don't yet understand, advancing our knowledge of organic chemistry, planetary science, and the potential for life in unexpected environments, all from a drone flying through orange haze on a moon nearly 1 billion miles away. Titan stands as one of the most fascinating moons because it combines atmosphere, liquids, organic chemistry, potential subsurface oceans, and geology into one world, a place that blurs the line between moon and planet, between familiar and alien. And studying Titan teaches us not just about Saturn's system, but about planetary processes, atmospheric dynamics, and the conditions that might precede life anywhere in the universe. Beyond Titan, Saturn has many other moons worth mentioning briefly, including Hyperion, a sponge-like moon with a chaotic tumbling rotation covered in strange, porous craters that give it a bizarre appearance, and Iapetus, a two-toned moon with one hemisphere bright white and the other dark as coal, divided by a mysterious equatorial ridge that rises 20 kilometers above the surface, one of the strangest geological features in the solar system. Iapetus's ridge runs almost exactly along the equator for over 1,300 kilometers, and no one knows how it formed, whether from tectonic forces, a collapsed ring, or material that accumulated along the equator. But standing on that ridge would be extraordinary, looking down slopes that drop 20 kilometers to plains below, seeing half the moon bright with ice and the other half dark with organic material, a divided world that defies easy explanation. Other moons like Rhea, Dione, and Tethys are icy worlds with subtle geological activity, showing fractures, craters, and possible cryovolcanism, and each one adds to the diversity of Saturn's system, creating a collection of satellites that spans sizes, compositions, and histories, from tiny ring shepherds to giant Titan, from dead Mimas to active Enceladus, a family of moons as complex and varied as any in the solar system. Now we leave Saturn behind, moving farther from the Sun, toward the ice giants Uranus and Neptune, where temperatures drop even lower, where moons are fewer and less explored but no less interesting, and where strange worlds await, from Miranda's cliffs to Triton's geysers, from Uranus's tilted system to Neptune's captured wanderer, distant realms at the edge of the planetary domain. As we drift outward, we carry memories of Saturn's rings and moons, of shepherd moons sculpting ice, of Enceladus's geysers venting an ocean, of Titan's methane rain and orange haze, a system that taught us moons can have atmospheres, liquids, and organic chemistry, expanding our sense of what's possible, what's habitable, and where we might one day explore. Uranus is unique among planets because it rotates on its side, tilted 98 degrees, so its poles point toward the Sun during its long seasons, and this extreme tilt extends to its moons and rings, which orbit almost perpendicular to the plane of the solar system, creating a system that looks like a bullseye from certain angles, rings and moons circling vertically, a sideways world spinning through space. This tilted system means Uranus's moons experience extreme seasonal variations, with each pole spending 42 years in continuous sunlight, then 42 years in darkness, as Uranus orbits the Sun in 84 years, and this bizarre lighting creates temperature differences, weather patterns if atmospheres existed, and erosion cycles unlike anything in Saturn's or Jupiter's systems, making Uranus's moons climatically unique. Uranus has 27 known moons named after characters from Shakespeare and Alexander Pope, and 5 are large enough to be rounded by their own gravity, the so-called classical moons, Miranda, Ariel, Umbriel, Titania, and Oberon, each icy, each shaped by impacts and possibly tidal heating in the distant past, though none are currently as active as Europa or Enceladus, making them frozen snapshots of ancient processes. We know relatively little about these moons, because only Voyager 2 has visited Uranus, flying past in 1986, capturing the only close-up images we have. And those images revealed worlds more geologically complex than expected, especially Miranda, whose fractured terrain suggests a violent history of tidal heating, impacts, or perhaps even reassembly after being shattered, though the details remain speculative and uncertain. Miranda is the smallest and innermost of the classical moons, only about 470 kilometers across, and its surface is a patchwork of different terrains, including strange features called coronae, oval regions with concentric ridges, and the famous Verona Rupes, a cliff that rises 20 kilometers, the tallest known cliff in the solar system, a sheer drop that would take about 10 minutes to fall in Miranda's weak gravity, a descent into darkness. Standing at the edge of Verona Rupes would be terrifying and exhilarating, looking down a cliff face that disappears into shadow far below. And if you jumped, you'd fall slowly, almost floating, accelerating gradually in Miranda's tiny gravity, about 1% of Earth's, drifting downward for minutes, watching the cliff face slide past, until finally you'd land gently, able to survive the fall because your terminal velocity in such weak gravity, even with no atmosphere, would be survivable, though deeply unnerving. Miranda's geology suggests it was once tidally heated, perhaps locked in an orbital resonance with other moons that flexed and warmed its interior, allowing geological activity, cryovolcanism, tectonics. But then the resonance broke, the heating stopped, and Miranda froze mid-process, preserving features that were still forming, like a sculpture abandoned half-finished, giving it the bizarre patchwork appearance that makes it one of the most visually striking moons. Uranus would hang in Miranda's sky, sideways relative to the solar system's plane, a pale blue-green sphere about 10 times wider than our moon appears from Earth, banded faintly with atmospheric features, and depending on the season, you might see Uranus's rings edge on, or tilted or face on, slowly shifting orientation as the years pass, a view utterly unlike anything seen from Jupiter's or Saturn's moons. The other Uranian moons are less dramatic but still intriguing. Ariel has long rift valleys and smooth plains, suggesting past geological activity. Umbriel is uniformly dark and heavily cratered. Titania is the largest, with some young features indicating past resurfacing, and Oberon is ancient and heavily scarred, and together they form a system that hints at complex histories shaped by tidal interactions, impacts, and perhaps brief periods of internal warmth. Future exploration of the Uranus system is being planned, with mission concepts for an orbiter in the 2030s or 2040s, and such a mission would spend years studying Uranus and its moons, mapping surfaces in detail, measuring magnetic fields, analyzing atmospheric composition, searching for subsurface oceans, and answering questions left open since Voyager 2's brief flyby nearly 4 decades ago, finally giving these distant moons the attention they deserve. Imagine orbiting Uranus and flying past Miranda, seeing the cliff face of Verona Rupes from above, photographing the coronae and fractured terrain, studying the color variations that hint at compositional differences, and then moving on to Ariel, Umbriel, Titania, and Oberon, building detailed maps, understanding how tidal heating shaped their histories, determining whether subsurface oceans exist beneath their icy shells, expanding our knowledge of ice worlds and their evolution. Now we move outward, one final step to Neptune, the outermost planet, where the sun is 30 times dimmer than from Earth, where temperatures are the coldest in the planetary system, and where the largest moon, Triton, orbits backward, a captured Kuiper Belt object, geologically active despite the cold, erupting nitrogen geysers, and doomed eventually to spiral inward and be destroyed by Neptune's gravity in a catastrophic collision millions of years hence. Neptune has 14 known moons, but Triton dominates, larger than Pluto, and the only large moon in the solar system with a retrograde orbit, meaning it orbits opposite to Neptune's rotation, proof that it didn't form alongside Neptune but was captured later, torn from the Kuiper Belt by Neptune's gravity, pulled into an elliptical orbit that gradually circularized, though tidal forces continue pulling it inward even now, a moon living on borrowed time. Triton's capture was likely violent, disrupting Neptune's original moon system, possibly destroying earlier satellites, scattering debris, and Triton itself would have experienced extreme tidal heating during the capture process, melting its interior, possibly creating a temporary subsurface ocean, though today Triton is cold and mostly frozen, with only traces of internal activity remaining, fading echoes of a warmer past. Triton is about 2,700 kilometers across, slightly smaller than Earth's moon, and its surface is the coldest measured in the solar system, around -235 degrees Celsius, so cold that nitrogen freezes solid, coating the surface in nitrogen ice that sublimes and refreezes seasonally, creating a dynamic landscape despite the extreme cold. A world still changing, still active, powered by faint sunlight and residual internal heat. The surface shows diverse terrain, including the famous cantaloupe terrain, a region covered in strange polygonal patterns resembling the texture of a melon's skin, formed perhaps by diapirs, blobs of warm ice rising through colder ice, or by cryovolcanism. And there are smooth plains, impact craters that have been partially erased by resurfacing, and dark streaks left by nitrogen geysers, evidence of ongoing geological activity despite the frigid temperatures. Voyager 2 discovered active nitrogen geysers on Triton in 1989. Plumes of nitrogen gas and dark particles erupting from beneath the surface, driven by sublimation of nitrogen ice warmed by sunlight, even the faint sunlight at Neptune's distance, and these plumes rise 8 kilometers high, then are blown downwind by Triton's thin atmosphere, depositing dark material in long streaks across the icy surface, visible from space. These geysers are cryovolcanic, eruptions of volatiles rather than molten rock, and they show that even in the coldest regions of the solar system, geological activity persists, driven by solar heating, tidal forces, or residual internal warmth, and Triton's activity makes it one of the few geologically active moons, alongside Io, Europa, and Enceladus, each active for different reasons, each teaching us how worlds stay alive. Standing on Triton would be profoundly cold and alien. The surface beneath your boots would be nitrogen ice, hard as rock, and you'd see dark streaks painted across white plains, marking where geysers have erupted, and overhead Neptune would loom enormous, pale blue with dark storms, about 6 times wider than our moon appears from Earth, but appearing smaller than Jupiter does from its moons, because Neptune is farther, more distant, but still magnificent and dominating. Triton has a thin nitrogen atmosphere, only about 70 microbars at the surface, about 70,000th of Earth's atmospheric pressure, barely enough to scatter light, and clouds occasionally form, thin hazes of nitrogen ice crystals drifting in the tenuous air, subliming and refreezing, and the sky would be nearly black, stars visible even in daylight, the sun a distant point of light 30 times fainter than from Earth. The gravity would feel familiar, about 8% of Earth's, stronger than most moons we've visited except Ganymede and Titan, and you could walk almost normally with only slight bouncing, and you might hike across cantaloupe terrain, stepping over ridges and depressions, wondering what internal forces created these patterns, what heat remains inside this captured wanderer still resisting the cold. Triton's fate is sealed by orbital mechanics, because its retrograde orbit means tidal forces continuously drain energy, pulling it closer to Neptune, and in perhaps 3 to 4 billion years, Triton will cross the Roche limit, the distance where tidal forces overcome its internal strength, and it will break apart, shredding into a ring around Neptune, a temporary, spectacular structure before the debris eventually spirals into the planet. Future missions to Neptune are being considered. Mission concepts for an orbiter that would study Neptune and Triton together, and possibly a lander for Triton's surface, studying the geysers, analyzing the ice, searching for organic molecules, measuring internal heat flow, and determining whether Triton still has a subsurface ocean from its capture heating, or if it's now frozen solid, a question that requires close study, instruments on the surface, and years of patient observation. Imagine standing at a geyser site on Triton, instruments recording temperature, pressure, composition, watching the ground shake slightly, feeling vibrations through your boots, and then a plume erupts nearby, nitrogen gas venting through a crack, carrying dark particles upward into the thin atmosphere, and you sample the material, analyzing it for organics, for clues about Triton's interior, for evidence of chemistry happening beneath this frozen surface. Neptune's other moons are much smaller and less remarkable, except for Nereid, which has the most eccentric orbit of any large moon, ranging from 1 million to 9 million kilometers from Neptune, taking nearly a year to complete one orbit. And this extreme ellipse suggests Nereid is a captured object, possibly disturbed during Triton's capture, flung into its current strange orbit by gravitational interactions billions of years ago. The other small moons orbit close to Neptune, several discovered recently by telescopes analyzing archival images, and these tiny irregular moons are likely captured Kuiper belt objects, dark and primitive, and they remind us that the outer solar system is populated by countless small bodies, some bound to planets, others drifting freely, remnants of the solar system's formation scattered across vast distances. Now, we move beyond Neptune into the realm of dwarf planets, where Pluto orbits with its family of 5 known moons, and the largest, Charon, is so massive relative to Pluto that they form a binary system, orbiting a common center of gravity that lies between them, not inside Pluto, making them partners rather than planet and moon, locked in an eternal dance, forever facing each other. Charon is about 1,200 kilometers across, roughly half Pluto's diameter, and the two are tidally locked to each other, meaning Pluto always shows the same face to Charon, and Charon always shows the same face to Pluto, frozen in mutual gaze, and from Pluto's surface, if you stood on the hemisphere facing Charon, you'd see that moon fixed in one spot in the sky, never rising, never setting, eternally hanging there, a constant companion. From the opposite hemisphere of Pluto, Charon would never be visible, permanently hidden below the horizon, and people living there would never see it, knowing it exists only by faith or instruments, a strange division where half the world sees the moon and half does not, separated by geography into two distinct experiences of the sky, two perspectives on their binary nature. New Horizons flew past Pluto and Charon in 2015, revealing worlds more complex and beautiful than expected. Pluto with its heart-shaped nitrogen ice plain, mountains of water ice, and reddish tholins coating ancient terrain, and Charon with a dark polar cap, possible cryovolcanic features, and a massive canyon system that encircles the moon, a fractured world that experienced tidal heating early in its history before locking with Pluto. Pluto's other moons, Styx, Nix, Kerberos, and Hydra, are much smaller, irregularly shaped, probably formed from debris scattered during the giant impact that created the Pluto-Charon binary, and they orbit in the same plane, tumbling chaotically, and their surfaces are likely water ice, bright and reflective, tiny worlds caught in the gravitational dance of their larger companions, witnesses to a collision billions of years ago. These distant moons at the edge of the planetary system remind us that moons exist wherever gravity allows, from the sun's warmth to the cold darkness beyond Neptune, and each one tells part of a larger story about how planets and moons form, interact, and evolve, creating systems within systems, hierarchies of influence, family trees of gravitational bonds stretching across millions of kilometers. Beyond the regular moons we've visited, each planet with giant gravity also holds dozens or hundreds of irregular moons, small captured objects orbiting in elliptical or retrograde paths, tumbling rocks pulled from the asteroid belt or Kuiper belt, bound loosely to their planets, some destined to escape eventually, others to crash, all temporary on geological timescales, transient members of planetary families. Jupiter alone has over 50 irregular moons, small dark objects orbiting far from the planet in distant eccentric paths, and Saturn has similar populations as do Uranus and Neptune, and these irregular moons are interesting because they preserve primitive material, unaltered since solar system formation, and they tell us about the early conditions, the chaos of planetary migration, and the violence of gravitational capture. Retrograde orbits mean a moon orbits opposite to the planet's rotation, and this is a clear sign of capture because moons forming naturally orbit in the same direction as their planet spins. And retrograde motion shows the object was captured later, pulled in by gravity during a close encounter, perhaps slowed by collisions with other objects, or by gas drag in the early solar system when atmospheres extended farther. Prograde irregular moons orbit in the same direction as their planet rotates, but still on elliptical and tilted paths. And these too are likely captured, just from different trajectories, and studying their orbits helps astronomers reconstruct the history of planetary migration, when giant planets moved through the early solar system, scattering asteroids and comets, capturing some, ejecting others into interstellar space. How moons form is a story with several chapters, some formed alongside their planets from the same disk of material, condensing and coalescing in orbit, and these regular moons orbit in neat circular paths aligned with their planet's equator, like miniature solar systems following the rules of angular momentum and gravity, orderly and predictable, born from the same cloud that made their parent planet. Other moons formed through giant impacts, like Earth's moon born from the collision with Theia, or Pluto Charon created by a massive impact in the Kuiper Belt. And these moons are large, often locked tidally, composed of material from both bodies, and their existence teaches us that violence is part of planetary evolution, that impacts don't just destroy, they also create, forging new worlds from catastrophe. Captured moons are the third category, pulled into orbit from elsewhere, and these show irregular orbits, diverse compositions, and they're common around giant planets whose gravity is strong enough to capture passing objects, especially during the early solar system when planets were migrating, stirring up populations of asteroids and comets, creating opportunities for capture that rarely happen today in our quieter, older system. Moon diversity across the solar system is staggering, from volcanic Io to methane rain Titan, from ocean world Europa to ancient Callisto, from geyser-spouting Enceladus to backward orbiting Triton, and this diversity arises from differences in composition, distance from the sun, tidal heating, impact history, and internal structure, making each moon unique, each a different experiment in how matter organizes under gravity. Some moons are geologically active, and tidal heating is the key, the flexing caused by gravitational interactions with their planet and neighboring moons, generating heat through friction, melting interiors, driving volcanism or cryovolcanism, and maintaining subsurface oceans. And this activity makes certain moons prime targets for astrobiology, because where there's liquid water and energy, there might be life. Simple perhaps, but life nonetheless. Other moons are geologically dead, either because they formed cold and stayed cold, or because they exhausted their internal heat long ago, and these moons preserve ancient surfaces, cratered and unchanged for billions of years, valuable as time capsules, recording the early solar system's bombardment history, showing us what surfaces looked like before erosion, tectonics, or resurfacing erased the record. The habitability question focuses on a few key moons: Europa, Enceladus, and possibly Titan, because these have liquid water oceans, energy sources, and complex chemistry, the ingredients we believe are necessary for life. And studying these moons has become central to astrobiology, shifting the search for life beyond Mars to the ocean worlds of the outer solar system, places we once thought too cold and distant to matter. What might life look like in Europa's ocean or Enceladus's sea? Probably simple, single-celled organisms, chemosynthetic bacteria analogous to those around Earth's hydrothermal vents, converting chemical energy from minerals into biological energy, reproducing slowly, perhaps forming biofilms or floating in the water, colorless because there's no sunlight to drive pigmentation, adapted to high pressure, cold, and darkness, life utterly unlike the familiar forms on Earth's surface. Imagine a submarine exploring Europa's ocean, descending through kilometers of dark water, illuminating the descent with lights, passing through layers of different temperature and salinity, and finally reaching the seafloor, rocky and fractured, where hot, mineral-rich water vents from cracks, and around those vents microbial mats sway gently in the current, orange or white or translucent, sustained by chemistry, thriving in isolation, a biosphere that evolved independently, proving life is not an Earth-specific phenomenon but a universal response to certain conditions. Or imagine drilling through Enceladus's ice, kilometers of frozen water, hard and cold, slowly melting a path downward, until finally the drill breaks through into liquid and a camera lowers into the dark sea, revealing particles drifting organic molecules, perhaps even cells, captured by filters and brought to the surface for analysis. A moment when humanity discovers life beyond Earth, not on a distant exoplanet, but in our own solar system, on a tiny moon orbiting Saturn. Comparing moon systems helps us understand why some planets have many moons and others few. Jupiter and Saturn have extensive systems because their strong gravity captured material and their distance from the Sun allowed ice to be abundant in their formation regions, creating conditions for many moons to form and persist. While Mars has only 2 tiny moons because it's smaller, less massive, and its location in the inner solar system made large moon formation unlikely. Earth is unusual for a terrestrial planet, having a large moon relative to its size, and this is likely due to the giant impact, a rare event that gave Earth a companion, and that Moon has stabilized Earth's axial tilt, moderated climate variations, created tides that shaped coastlines, and possibly influenced the evolution of life, making our Moon not just scenery, but a player in Earth's biological history, an unsung architect of habitability. Our journey through the solar system's moons has been shaped by exploration history, beginning with Galileo in 1610, observing Jupiter's 4 largest moons through his telescope, proving not everything orbits Earth, and continuing through centuries of telescopic observation, sketching surfaces, measuring orbits, discovering new satellites, slowly building a catalogue of these distant companions, each discovery expanding our sense of the solar system's complexity. The space age revolutionized our understanding. With the Voyager missions in the late 1970s and 1980s flying past Jupiter, Saturn, Uranus, and Neptune, sending back the first close-up images of moons previously seen only as points of light, revealing volcanic Io, fractured Europa, giant Ganymede, cratered Callisto, shepherd moons in Saturn's rings, geysers on Triton, and landscapes more diverse than anyone predicted, transforming moons from abstractions into worlds. Voyager 1 and Voyager 2 launched in 1977, taking advantage of a rare planetary alignment that allowed them to visit multiple worlds using gravity assists, and they're now in interstellar space, still transmitting faint signals, but their legacy lives in the images and data that revealed the outer solar system's richness, inspiring generations of scientists and engineers to continue exploring, designing missions to return, to orbit, to land, to study these worlds in greater detail. The Galileo spacecraft orbited Jupiter from 1995 to 2003, conducting dozens of flybys of the Galilean moons, mapping surfaces, measuring magnetic fields, detecting subsurface oceans, watching Io's volcanoes erupt, analyzing Europa's icy crust, and transforming our understanding of these moons from brief Voyager snapshots to detailed studies, proving that long-term orbital missions yield far more science than quick flybys, establishing a model for future exploration. Cassini orbited Saturn from 2004 to 2017, an even longer mission that revolutionized our understanding of Saturn's moons, discovering Enceladus's geysers, studying Titan's atmosphere and lakes, mapping ring moons, analyzing ice composition, and revealing the diversity of Saturn's system. And its deliberate plunge into Saturn at mission's end prevented contamination of potentially habitable moons, a sacrifice that protected the worlds it studied, ensuring future missions could search for life without interference from Earth organisms. New Horizons flew past Pluto in 2015, after a 9-year journey revealing a geologically active dwarf planet with a complex moon system, and it continues outward, flying past Kuiper Belt objects, studying the solar system's edge and its images of Pluto's heart-shaped plane and Charon's fractured surface showed that even in the coldest reaches, worlds remain dynamic, surprising, beautiful, and worth exploring, expanding the frontier of human knowledge into the realm beyond Neptune. Currently, the Juno spacecraft orbits Jupiter, studying the planet's interior and magnetic field, and during extended missions, it conducts flybys of the Galilean moons, imaging their surfaces at high resolution, measuring gravity fields, adding to our knowledge with modern instruments, building on Galileo's foundation, and demonstrating that even well-studied moons still hold secrets, still reveal new features when observed with better technology and fresh perspectives. Future missions are planned or proposed for multiple moons, with Europa Clipper launching in the 2024, scheduled to arrive at Jupiter in the 2030s, conducting dozens of close flybys, mapping Europa's ice shell, measuring ocean depth, analyzing plume composition, and identifying landing sites for future missions that might drill through the ice, sample the ocean, and search for life. A multi-decade campaign to explore one of the solar system's most promising habitable environments. The JUICE mission, launched in 2023, will arrive at Jupiter in 2031, studying Ganymede, Europa, and Callisto, with emphasis on Ganymede, where it will eventually enter orbit, becoming the first spacecraft to orbit a moon other than our own. And it will map Ganymede's magnetic field, study its subsurface ocean, analyze surface composition, and coordinate with Europa Clipper to provide complementary data, together transforming our understanding of Jupiter's ocean moons. Dragonfly will launch in the late 2020s, arriving at Titan in the mid-2030s. And this rotorcraft will fly through Titan's thick atmosphere, hopping between sites, studying organic chemistry, sampling surface materials, analyzing lakes and dunes, searching for prebiotic molecules, and testing whether Titan's environment could support exotic methane-based life or preserve clues about how life began on Earth billions of years ago. A mobile laboratory exploring an alien world's surface and skies. Proposed missions include orbiters for Uranus and Neptune, landers for Enceladus and Triton, sample return missions from Martian moons, and even concepts for submarines to explore Europa's or Enceladus's oceans. And while these missions are years or decades away, they represent a long-term commitment to exploring the solar system's moons, recognizing them not as mere satellites but as worlds, each deserving study, each holding pieces of the puzzle of planetary formation, evolution, and habitability. Why we study moons extends beyond pure curiosity. They teach us about planet formation, because moons preserve records of early solar system conditions. They teach us about habitability, because some harbor oceans and energy sources, and they teach us about resources, because future space exploration will require water, fuel, and materials found on moons, making them not just scientific targets, but strategic assets for humanity's expansion into space. Moons are time capsules. Some, like Callisto, preserve ancient cratered surfaces unchanged for billions of years, recording the late heavy bombardment, while others, like Io or Enceladus, constantly renew themselves, erasing history, showing us active processes, and together they span the range from frozen past to dynamic present. From museum displays to living exhibits, each contributing to our understanding of how worlds work, how they age, how they stay alive or grow quiet. The search for life beyond Earth has shifted focus from Mars's surface to the ocean moons, because while Mars may have hosted life billions of years ago, Europa and Enceladus might host life right now, hidden beneath ice, sustained by chemistry, and discovering even microbial life there would answer one of humanity's deepest questions, proving we are not alone, that life arises wherever conditions allow, and that the universe might be filled with biology waiting to be found. Imagine a future where humans live on Titan, in habitats protected by thick atmosphere, mining hydrocarbons for fuel and materials, studying prebiotic chemistry in lakes, and serving as a base for exploring the outer solar system. Or imagine robots swimming in Europa's ocean, sending back images of hydrothermal vents, tracking microbial blooms, documenting an alien ecosystem, or picture mining operations on Callisto, extracting water ice, processing it into rocket fuel, supporting missions that venture farther to the Kuiper Belt and beyond. These futures may seem distant, but they begin with the missions launching now, with the data we collect, the technologies we develop, the knowledge we accumulate, step by step, moon by moon, building understanding that will guide humanity's expansion into the solar system, transforming us from inhabitants of one world to explorers and eventually residents of many worlds, a transition already beginning with robots as our pioneers. Tonight, when you look up at Earth's moon, hanging bright in the dark sky, remember it's one of over 200 moons orbiting through our solar system, each unique, each with its own story, from volcanic fire to frozen ocean, from methane rain to nitrogen geysers, from ancient craters to fresh ice. And that pale light you see reflected from our moon is part of a larger family, satellites bound to planets, partners in gravitational dances, witnesses to solar system history. Each moon we've visited tonight tells a different story. Io shows us tidal heating's power, Europa whispers of hidden oceans, Ganymede demonstrates magnetic complexity, Callisto preserves ancient time, Enceladus erupts with possibility, Titan rains hydrocarbons under orange haze, Miranda's cliffs defy explanation, and Triton orbits backward toward its doom, a collection of worlds as diverse as the planets themselves, each worth a lifetime of study, each holding secrets. As this journey comes to a close, I hope you found it calming, informative, or restful, whatever you needed tonight, and I hope the slow pace and gentle rhythm gave your mind space to wander among these distant worlds, imagining what it would feel like to stand on each surface, looking up at giant planets or down at alien seas, experiencing the solar system not as numbers and facts, but as places, real places, waiting quietly in the darkness. The moons will continue orbiting long after we're gone, patient and silent. And they'll welcome future explorers, robots and humans, who will walk their surfaces, study their secrets, perhaps even find life hidden in their depths. And those discoveries will change how we see ourselves, proving we are not alone, or proving we are unique. Either answer profound, either outcome transforming humanity's understanding of existence, meaning, and our place in the cosmos. So take a slow breath, let your thoughts settle like dust on an airless moon, and know that you've traveled tonight through the solar system's family of satellites, from Earth's familiar companion to Neptune's captured wanderer, visiting volcanic moons and frozen ones, active worlds and dead ones, ocean moons and desert moons, a tour through 200 worlds, each contributing to the grand story of how matter organizes, how gravity shapes, and how the universe creates complexity from chaos. Picture yourself drifting peacefully through space, floating past each moon in your mind, seeing Jupiter shrink behind you, Saturn's rings glinting ahead, Uranus tilted on its side, Neptune pale blue in the distance, and beyond them all, the stars. And as you drift, the images soften, the details blur, the names fade, and you're left with a feeling, a sense of wonder, of vastness, of connection to something larger than yourself, and that feeling carries you gently towards sleep. Rest now, knowing the moons are still there, still orbiting, Io still erupting, Europa's ocean still flowing, Enceladus still venting geysers, Titan still raining methane, all continuing their ancient rhythms, indifferent to our attention, but enriched by our curiosity. And perhaps someday you'll look up at our moon and remember tonight's journey and feel connected to that larger family, those distant companions orbiting silently through the solar system's darkness, waiting patiently for the next visitor to discover their stories. Sleep well, and let your dreams carry you across icy plains and methane seas, beneath frozen shells and orange haze, to places where gravity is gentle, where silence is complete, where Earth is just a distant point of blue light, and where the universe reveals itself slowly, one moon at a time, one detail at a time, one peaceful breath at a time, until thought dissolves into rest, and rest dissolves into sleep, and sleep carries you softly into the quiet dark, where moons drift eternal, and all is still, and all is well.